Good afternoon to all of you. Today we are, this program we are going to look at design of beams. So it's actually a small topic, but there are so many things involved in beams that we need to have a full session only on beams. So the content will be like this. Today I'll be covering elastic and plastic analysis of beams, and then after that something called laterally restrained beams. Then I'll be proceeding tomorrow to laterally unrestrained beams and design of plate girders. So in laterally unrestrained beams, a small part will be covered on gantry girders. As such, gantry girders are basically laterally unrestrained beams, and they do have, of course, some problem because of the impact factors and the fatigue induced by the cranes. And then plate girders are deep girders which are used for large spans and when the loads are very heavy. And then we will, the day after, that is the third day, we will go to something called beam to column connection. So once you design a beam, you will have to connect it to the column. So how do you do that? We are not going to go into details of the bolt design or the weld design, etc. That was covered in the previous workshop. So you can have a look at that. But we are going to just have a look at what are the typical beam to column connections which are used. And then we will have a tutorial session where we will solve examples on laterally unrestrained beams and plate girders. So that is the third day. Today, in case time permits, we will quickly go through a Word file on a worked example on laterally restrained beam, just to show you how the design is to be written down. Okay. So with that, I think I'll go ahead with this presentation. This is elastic and plastic analysis of beams. So basically, the idea is that you can't design a beam properly or economically unless you are aware of what are the results that you are getting from your analysis and how to manipulate those results so that you get safer designs, safer and economical designs. Economy is a prime factor in design. Okay. So the contents of this lecture are like this. First, we will look at the theory of pure bending. It's actually a very commonly used theory, but many of you would have learnt it in your strength of materials course also. So, but then when you bring it to the design of beams, you have to understand some other issues related to that. Okay, and then we will proceed to elastic analysis of beams. So where we will analyze some standard beams, and then based on that we will work out the solutions, because I often find that people design beams without knowing the basic solutions and the implications of the end conditions, etc. Then once we go through that, we proceed to plastic analysis of beams, and we'll just touch upon portal frames, rectangular portal frames, and then finally we'll go to limit state design of beams and frames. So what are the actually, we are not going to cover the detailed codal provisions in this lecture, but we will cover it in the next lecture, that is laterally restrained beams, etc., etc., and the other subsequent lectures. So basically, elastic theory of pure bending goes like this. We apply a bending moment to a segment of a beam of flexural rigidity EI, where E is the Young's modulus and I is the moment of inertia of the cross section. And we apply this bending moment. So there are two couples, or two movements equal and opposite in direction, and as a consequence the beam bends in the shape of in the arc of a circle with a radius as r, and 1 upon r is known as the curvature of the beam. Okay. So we just want to analyze this. We are going to assume that the shear forces are negligible, so it is called pure bending without shear force. And then as a consequence, we say that we can see here itself that what would have been a nice rectangle, straight rectangle, has now bent into an arc, and the edges of the rectangle are now basically parallel to they continue to remain along the radius vector. Okay. So this condition, that is produces what is called as linear strain variation. So we say that the fundamental assumption in theory of pure bending is that plane sections before bending remain plane after bending, and the strain, consequently the strain varies linearly with the distance y from the neutral axis. So there will be a neutral axis at which the strain will be 0, and above the neutral axis you might have, let's say, compressive strains. Below the neutral axis you will have tensile strains, and the strain varies linearly as you go away from the neutral axis by a distance y. Okay. So for linearly elastic materials, so this is another condition which is required. This is called the material stress strain curve, or the constitutive modeling of the material. So since the material is assumed linearly elastic, the stress F varies linearly with strain. So if this is my strain variation, my stress variation will come like this. Okay. So stress also varies linearly with the distance y. So the neutral axis will be such that the integral of the stress over the entire area is 0. That is, you have the stress above the neutral axis, which is compressive, which is negative, let's say, and the stress below the neutral axis tensile, which is positive. So if you integrate it over the whole area, you have to get 0. And since F is proportional to y, and the moment of the force FdA, that is, if you take a small elemental area dA in the cross section here, it is proportional to its distance y. That is, the stress is proportional to the distance y. Its component, that is, its moment component, becomes stress into y. Okay, so one more y will come. So indirectly it will become integral of y squared dA, and this properties of the shape of the cross section is called the moment of inertia of the section. Thus we get moment of resistance m is equal to EI by R, okay, where I is the moment of inertia of the cross section. So of course you know how to calculate the moment of inertia about a given axis. Let's say in this case it will be the neutral axis. So based on that you can calculate this. This is also written here in a different way in the top, that is m by I is equal to F by y, where F is the stress at a distance y, and this is equal to E by R, where E is the Young's modulus and R is the radius of curvature. Okay. So we realize that as far as the first part is concerned, if m that can be resisted is basically F into I by y, so it is a function of the cross section and a function of the stress that the material can take. Okay. So the limiting value will be the yield stress, because it's a linearly elastic material. So we know that most materials have a point called yield stress, so it cannot go beyond that. So we have to limit F to Fy. Okay. So I will get My, the limiting capacity, as Fy into I by y. This I by y max is called the elastic section modulus and is denoted by Ze. Okay. So that is the value of the cross section, which proportional to which the section can take the bending moment. Okay. So that is one part. The other part is F by I, m by I is also equal to E by R, or in other words m is equal to Ei by R. Okay. So 1 upon R, as I said, is called the radius of curvature. So it is basically, it's denoted by phi, so it is Ei into phi. Okay. So we realize there is a question here. It says if a steel and a wooden beam of same section are subjected to same bending moment, so m is same, I is same, y max is also same. Okay, which beam will have more stress and which beam will deflect more? So if that is the case, obviously both the beams will have the same stress F. Okay, so that is the first part of the answer. And which beam will deflect more? The one which has a larger radius of curvature will probably deflect more. In this case, we know that wooden beams have smaller Young's modulus compared to steel beams. So obviously the wooden beam will deflect more. So you have a visual confirmation of what is happening. Whereas in steel beams the E values are very high. So what happens is you don't really see the deflections. Okay, so you know that it has deflected, but you don't normally under small bending moment you can't see the beam deflecting appreciably. Okay, so that is one. The second question is, now if F that is Fy, that is the yield strength, is increased, obviously the moment capacity will go up. So if you have a higher strength steel, so I'll have my moment capacity or moment of resistance, as we call it, is Ze, that is I by y is Ze into Fy, right? So where if I increase Fy, let's say for mild steel Fy will be about 250 MPa, whereas for high strength steel it could be 350 or even up to 550 MPa and all. So if I increase F, I'll get a larger moment of resistance. okay. But then the E for steel doesn't change with the steel grade. So E for any grade of steel is typically 2 into 10 to the power 5 MPa. So E doesn't change. So what will happen is the deflections will not change. So if let's say my steel beam deflects by some value delta, then the high strength steel also will deflect by the same value delta. So we may not gain anything by going for high strength when deflection is governing the beam design. So this is very fundamental thing we have to be very clear before we start designing beams, because nowadays variety of steel grades are available, and people get confused. They think that if you use a high strength steel, you might get a economical design, but when your spans are large, loads are light, you may not get an economical design because still the deflection will be governing, okay. So that is something which we have to be very clear about, okay. So we proceed further with the elastic analysis. So basically there are something called Euler-Bernoulli beam equations which come out as a consequence of the theory of pure bending, and what they say is that the EI d fourth, that is fourth power, if y, let's say if I take x along the axis and y as the downward deflection, so the fourth derivative of y with respect to x is nothing but the is equal to the applied load, okay. In this case q of x, q denotes the UDL over at that point x, okay, the load at that point x. So in this case, let's say I have taken a simply supported beam under uniformly distributed load. So my q is constant, I denote it by small w, that is q is constant, that is shown here as this upper line with downward arrows. So that is my load on the beam, and if q is constant, then the shear force V can be obtained by integrating this equation. So integral of q x dx gives me V, and when I integrate the left hand side, it becomes EI d cube y by dx cube. And of course when you integrate in the real case, you will also get a integration constant, right. So you have to figure out how will you evaluate that integration constant, okay. I think span L has changed to lambda here, I don't know, due to some version problem. Basically here L is the span of the beam, now it is showing it as lambda. So the shear force V comes out as Wx, because we are integrating W into x plus an integration constant C, which we are going to evaluate by knowing the shear force at some point, okay. So since its loading is symmetric, we can say that, for example, the shear force at midspan will be 0. So if I put that at x equal to L by 2, V is 0, I get that constant C as minus L by 2. So my V becomes W into minus x minus L by 2, okay. So that is how I will get the shear force. Similarly, again going further, if I integrate the shear force V with respect to x, so this will become integral of V dx, so that gives me the bending moment at x, okay. And the left hand side obviously becomes EI d squared y by dx square, okay. So that is how this turns out. And if I again integrate, I mean find the integration constants, I know that at x equal to 0, for example, m is 0 because I have a hinge here, and mind you, in a simply supported beam you always have one hinge and one roller, okay. So the roller has to move little inwards for it to have the same length. This original length and the deformed length has to be same. So the fact that this has deflected downwards means this roller has to allow some movement inwards, which has a great consequence on design, later we will see. And as a consequence, if I put this, I get the constant again as 0. So m again becomes W by 2 into x squared minus Lx, okay. So that is my variation of the bending moment. And again, if I integrate further, we saw in the previous slide that 1 upon r is phi, and when you integrate phi over length, you get the theta, that is this theta, rotation angle theta. So that is basically nothing but the slope of the elastic curve, that is, this is called the elastic curve. So here we find that if we integrate further, we get the theta as given by this formula, and we find that for example, theta will be very high at the ends, and then it reduces to 0, and then it increases. We will look at the relationship between these diagrams once again, and let us complete this by integrating theta one more time. we can get the deflection at any point delta. So deflection delta at a distance x from the support is given by W by 24 EI into this formula, that is x raised to 4 minus this. So if you want to know what is the maximum deflection, you will have to put x as L by 2, and then you will get the standard formula, that is 5 by 384 WL raised to 4 by EI. Okay, so that formula you will get. So that is the deflection. So this gives you the complete solution for this beam. Okay, so these set of equations help you solve this beam very easily, and you get to know everything about the shear force diagram, the bending moment diagram, the slope diagram, and the deflection diagram. All these deflection diagram is also called the elastic curve because it is the shape that the beam will assume when it deflects. Okay, now it's very important for us to understand this relationship by also looking only at the figures. Okay, so here let's look at this. We have a uniformly distributed load, which means the slope of my shear force diagram has to be constant, and taking the downward load as positive, we also realize that the slope in this case has to be positive. That's why I have plotted the shear force diagram in this manner. So basically there will be a reaction here R, which is actually upwards, so which is negative in this case. So it produces, this is upwards and the load is downwards, so you have a sort of a clockwise shear force. So that is denoted as negative, and the anti-clockwise shear force becomes positive. Okay, so starting with a large anti-clockwise shear force, clockwise shear force, we find that as the studial is applied, we go on adding up those values. So this actually gets reduced, and then it becomes 0 when you reach the midspan, and then the shear force continues to increase and it becomes maximum at the other end. So basically it is actually the clockwise shear force value at the other end, okay, which will be W by 2 in this case. Both will be W by 2, okay, sorry, WL by 2. So this is my shear force that I have. Now with reference to this, we also need to understand how the bending moment varies. So bending moment of course has to satisfy the end conditions. All the forces or all the diagrams have to satisfy the support conditions. Okay, so here at the two ends the bending moment is 0. Starting with a 0 bending moment, the slope is high but negative, right? So it has to go down. The slope, the shear force is high but negative. So the bending moment diagram has to slope very steeply down, and then as it continues, the shear force becomes smaller and smaller. So the steepness will reduce until at this point the bending moment becomes maximum. So where the bending moment is maximum, the shear force is 0, and then you proceed ahead. Again the slope slowly goes on increasing, and then your bending moment becomes 0. But the diagram is steeply sloping upwards. Okay, which is what is the slope of the in the shear force diagram. Okay, so that is what we need to understand, and the bending moment basically tells you how the beam is going to bend. Okay, so if the bending moment is high, it will bend in a very sharp curvature, right? That is very small radius of curvature. If the bending moment is low, it will bend, it will be almost straight, right? So that is what we have to understand. So here we find that at the ends the bending moments are low, so the curvatures or the slopes would be fairly small, and then as we proceed, the slope of it should be very high, and then it will reduce to 0. Okay, so here it is very high, it comes down, but notice that this is going in a concave fashion, not in a convex fashion. So you have to understand that also. So it goes like this because the slope of this is this is my theta. So this is differentiated to get the bending moment diagram, right? So that is what we are getting here. So the slope becomes 0. When the BMD slope becomes 0, you get this as 0. Okay, and when this is high, it becomes high. And this is high but negative, this becomes high but negative, like that. Okay, so that is the slope diagram, and slope into let's say basically the distance dx, integral of theta dx will be my delta, right? So that is what is shown here as the delta diagram, and delta again has to satisfy the end conditions. So here, since these two are the supports, the delta has to be 0 at the two ends, and delta becomes maximum in this case at midspan. Okay, so that is how we get the deflection diagram. So, and this is what the Euler-Bernoulli equations tell us, and it looks pretty easy, But then when you apply this to complicated beams with different loads, you may find some difficulties, right? So that is one thing. But especially when this UDL becomes a point load, what will happen is the point load will bring in a discontinuity in the shear force diagram. So let's imagine a simply supported beam with a central point load. So what will happen is the shear force diagram will come like this, it will go like this, and it will suddenly go up due to that point load, and then it will go that side and come down. So it will become like two rectangles. So there is a slope discontinuity in the shear force diagram, and consequently there may also be a slope discontinuity in the bending moment diagram. So a bending moment diagram will look like an inverted triangle. There will be one slope here and suddenly slope will change and there will be another slope here. Okay, so that is how it will come. But then with reference to the slope and the deflection, there will be no discontinuity. So slopes and deflections are relatively continuous, only their differentials are discontinuous. Okay, so you might have studied in calculus about different functions which are differentiable. Okay, so it becomes sort of difficult to handle the shear force and bending moment diagrams by equations when you have a point load, but you can still handle them in slopes and deflection terms. Okay, so that is actually the basis for something called the slope deflection method. Okay, so when point load acts, there is discontinuity of shear force and bending moments, but slopes and displacements remain continuous. So that is the fundamental thing. The slopes and that slope deflection method becomes useful to solve indeterminate structures. So that is how the different methods have been evolved based on the convenience to apply it into a particular situation. Now here we are going to look at one such method which is very simple. This is just the method of superposition, because whenever a system or a beam is elastic, you can solve it as separate systems and then superpose those stresses, deflections, everything, bending moments, everything you can add up and to get the final values for the actual beam. Okay, so let's look at what is known as a propped cantilever. It's actually an indeterminate beam because the propped cantilever has support moment plus one more reaction, plus one reaction at the support fixed end. So there are two upward reactions and one moment, and you have only two equilibrium equations, that is the sigma vertical forces equal to 0 and sigma moments equal to 0. So you have only two equations, but you have three unknowns. So you need to find some other way to solve for the third unknown. Okay, and that's what we are going to do here. So what we are doing here is we are going to use the condition of compatibility. Compatibility means the deflections should be compatible to the support conditions and they should have continuity of slope, etc. Okay, so that is what it means. So what we are going to do is this propped cantilever, there is a roller here, and we are going to remove this roller. So it will become a regular cantilever, fixed end and a free end, subjected to UDL, and that is what is shown here. And under this W, we know that you can use the previous equations, Euler-Bernoulli equations, to solve this, and you will get the tip deflection as WL raised to 4 by 8 EI, where EI is the flexural rigidity of the beam. So if the support was not there, this beam would have deflected by this value at the free end, okay, downward deflection. And the corresponding bending moment diagram also is easy to add up. So you find that bending moment at the free end will be 0, and as we proceed towards the fixed end, we are going on adding this UDL. So we will be adding more and more values, so it becomes steeper and then it becomes high at this. So this is the fixed end moment and this is the free end which is 0, having 0 moment. So this is my bending moment diagram for this case. Now to this I am going to add another similar beam which is now having a reaction at B as the load, upward load. Okay, so when I apply a force RB, again I can solve this using the Euler-Bernoulli equations, and I get the deflection as RB into L cube by 3 EI. Okay, so this is the deflection, upward deflection that I get for this case, and the corresponding since it's a concentrated force, the shear force is constant throughout the length of the beam, and the bending moment will vary linearly consequently. And so basically it is RB into this distance from the free end, the lever arm, that will give me the bending moment at a point x. Okay, so that is this value, and that RB into L will be the fixed end moment at this end. Okay, so that is what I get. Now if I add these two bending moment diagrams, I will get the net bending moment diagram. So I have shown this inverted downward triangle upwards just to remove it, because we have to subtract it. So here from the total of the first case, this gets subtracted and what remains is the shaded part. But after this point, the second one has more value than the first one, so it goes upwards. Okay, so this is one way of showing the net bending moment diagram, and we find that somewhere here maximum sagging will occur and eventually the bending moment will become 0 at this point. This point incidentally is called the point of inflection, where the bending moment changes sign from sagging to hogging. So it is called a point of inflection, okay, as far as the elastic curve is concerned. So now looking at this, so now we know that for the prop cantilever at the free end, the deflection should have been 0. So we need to equate these two deltas to make that as 0, and as a consequence equating RB L cube by 3I to WL raised to 4 by 8EI, I will get RB as 3WL by 8. So that is the value I get for the support reactions. Once I know the support reaction, it is very easy for me to calculate the rest of the things. So I can calculate the bending moment at any point. For example, at this point it will be RB into X minus W into X is the load acting at X by 2. So that will minus Wx square by 2 will be the value. So RB into X minus Wx square by 2 will be the bending moment at any point. And when that becomes 0, we can find at what X it becomes 0 and so on. Okay, so that solves the prop cantilever problem. Again we realize that for compatibility we need to know the material property, which in this case is the Young's modulus, and the cross section property, which is the moment of inertia. Okay, but if you go back, you can see EI comes in these two equations. So for slope and deflection, but EI does not come in the shear force and bending moment, because they are depending only on equilibrium. They are not depending on the cross section of the beam or on the material of the beam. So whether I use a steel beam or a wooden beam, I will get the same variation for V and M, but my theta and delta will be different. Okay, probably the variation shape may be same, but the magnitudes will be different, right? So that is how we should understand that the two properties affect the deflection of the and the slope of the beam. Okay, so for using the compatibility condition, we must know the material constitutive relation, and as such the equilibrium equation, the compatibility conditions, and the material constitutive relation, in which case, in this case it is stress proportional to E into epsilon strain. So these three are the three pillars of structural analysis. So we use these three sets of equations to solve any problem. Okay, and in the case of elastic problems, we will say that F is equal to, stress is equal to E into epsilon, but that will not be valid once the material is inelastic or it goes beyond the elastic range. So as a consequence, we have to necessarily ensure that the stress for any beam remains within the elastic limit if we want to use elastic analysis. So that becomes a major limitation for this analysis. Okay, so now that is anyway one part, but then apart from that, it was realized that if you just reach that point, that is when you go on increasing the bending moment or the load or whatever, until some point in the beam reaches a stress Fy. Okay, so the elastic analysis is not valid beyond that point, but then nothing drastic happens to the beam. Okay, so what I mean is, like for example, if you take a wooden beam and you go on bending it, okay, so suddenly it will snap, it will break. Okay, so that is when you have just reached its limit, elastic limit. It's not able to take any stress beyond that, so it breaks. Okay, so it will snap suddenly. So that is, there are materials which are called brittle materials where elastic analysis has to be used and you can't go beyond that. But if you take a steel beam, you know that even if you bend beyond that elastic limit, actually you can't even see what is happening, right? If you bend quite a bit, then you will see that the beam has bent and it is not becoming straight again. But then when you take a beam and start loading it slowly, you will not even realize physically, you don't see anything happening when the beam reaches the yield limit, okay, that is my or whatever. So, so that is one thing, and if nothing happens, then can't we use the beam for taking higher loads? That is the next question, right? So we really find that significant post-elastic strength exists and efforts to use it to achieve economy. If you can use that strength which is beyond the elastic limit, then you will get an economical design for the beam. So this was realized in Europe after the Second World War, when they had to do a lot of rebuilding, and that led to the development of the so-called plastic analysis and design methods. Okay, so for steel, it is always advantageous to use plastic analysis and design methods rather than elastic analysis and design methods. It has nothing to do with whether your design is working stress method or limit state method. Basically, it's just an analysis and design method that we are following, and in limit state method, in either method, whether you use WSM or LSM, you need to ensure that the deflections etc. are within serviceable limits under working loads, and at ultimate loads the collapse is prevented. But that second criteria, when you use plastic analysis and show that collapse can be prevented, you will get a major economy. Okay, so that is what is an advantage. Now we compared wood with steel. Now let's see if we can compare an aluminum alloy beam with steel. Okay, so what happens with an aluminum alloy beam is that it has almost the same strength as steel, right? So let's say 250 MPa is the strength of the aluminum alloy, but its Young's modulus is drastically low. It is around 1/4 to 1/5 of steel, right? So its deflection would be very, very high. So most aluminum beams will fail due to deflection rather than by strength. So in such cases, again, we may not be able to use plastic analysis because we are within the elastic limit itself, we are having problems, and it's the deflection which is governing. So again, such instances, for example, even if it's a steel beam, if it's a very long span beam with a very low intensity of load, then it may not, it may be governed by the deflection limit. So in such cases, we will not have any advantage in going for plastic analysis. Okay, so those are other issues. So we need to understand all these implications before we go to the design of beams. Okay, now to understand plastic analysis, or let's first look at what happens to a beam when we load it beyond the elastic limit. So we take a simply supported beam, and what we will do is we'll apply a point load at the midspan, like W here, and as a consequence, the bending moment diagram which is shown here is inverted triangle. This you know is WL/4, where L is the span of the beam, and this is much less than my as of now. 1/5, the curvature diagram, that is, you know, m/I equal to E/R. So m/EI is the diagram which has been plotted as 1/R here. So this is proportional to the m, right? So that is why this is also similar, and it is within the elastic limit. And if I draw the moment versus curvature diagram, it will be a straight line. So since it's proportional, it will be a straight line. I continue to increase the W, and what I find is when I reach the bending moment at midspan reaches my, the yield moment. So at this point, the extreme points at the midspan section, they have just reached yield stress. Okay, actually I have shown it a little larger in red because it's actually a small dot. It's not even visible, but then I have just put it a little bigger, so just for clarity. But then nothing will happen to the beam, right? So this has just touched my. Only thing that will happen is beyond this point your elastic analysis is not valid. Okay, so you will, the deflection you calculate will not be valid. The bending moment will still be valid because it is based on the equilibrium condition. It has nothing to do with the material property, so it will remain valid. It will remain WL/4. Okay, so now I call this load as WY, corresponding to the midsection reaching my. Okay, so the bending moment here at this point will be WY into L/4, nothing different. So and then the curvature remains like that. So we have reached this point my. We further continue to increase the load, and gradual plastification will happen across the midsection, and also the plastifications will spread along the length. It will spread to a length such that points at which the bending moment is above my. So this is my my. So from here to here, the bending moment is more than my, right? So up to that point, the yield would have occurred along the length of the beam also. So this is called as plastification along the length of the beam, and as a consequence, when these two plastification zones meet, we say that a sort of a plastic hinge has formed, and the curvature diagram has a sharp kink at this point. Okay, so the M5 curve slowly goes on losing the slope until the slope becomes almost 0 at MP. So this point is called the full plastic movement of the section. So the entire cross section has plastified, and in fact you don't even have to increase the load any further. At the same load, what will happen is this beam will go on rotating, because now it is a plastic hinge. So under the same load, it's not a structure anymore, it is a mechanism. So this beam will go on deflecting downwards, and then this curvature will go on increasing. It will almost go towards infinity, right? It will not really become infinity, but it will be very high basically. Okay, so we say that the beam has failed, but it will never break like your wooden beam or brittle material beam, right? So it will not be like that. In fact, to demonstrate this, we actually do a lab test in our lab. We just take a square steel rod, make it a prop cantilever, we go on applying the load. The fixed end yields and forms a plastic hinge. The load point under the load yields and forms a plastic hinge. Then the mechanism forms, and then the last weight when they put, the beam goes on deflecting and it doesn't come back. Okay, so that is the point of failure. In real materials, after you cross the yield plateau, there is strain hardening happening. So the deflection will not become infinite, it will remain at some point. Okay, so that is, but anyway, the beam has failed. So this is called the elastic plastic behavior, and we need to now develop a theory to use this and calculate the collapse loads that beams can take. Okay, so what is the value of WP and with reference to WY that the beam can take. Okay, so that is what we are now looking at. At the cross section level, this is what happens. If I take an I section, when the movement is less than the yield movement, so you have a stress at the extreme fiber which is less than, this is small Fy, the yield stress, and then as the movement becomes the first yield movement, the stress just reaches Fy, and when the movement becomes more than My, there is gradual plastification across the section. So up to here the section has plastified, but this is still elastic, the core is still elastic, and this becomes steeper and steeper until it almost becomes flat. That is when you say that your cross section has reached the full plastic movement MP. Okay, so that is what we are looking at, and the value of MP can be directly calculated as a consequence of this stress distribution. So we have a stress distribution over some part of the, let's say the upper half of the beam. Okay, all the elemental areas are under yield stress. So if you take dA into Fy, that is the stress resultant for that area, elemental area, and that into its lever arm from some neutral axis will give you the moment contribution. Okay, so basically since the entire upper part is under, let's say minus Fy, and the entire lower part is under plus Fy, that is tension, the other one is compression. So Fy into this area gives me the stress resultant C, capital C. Similarly, Fy into this resultant gives me the capital T, and since C has to be equal to T, we conclude that these two areas have to be equal. So the plastic neutral axis is also called the equal area axis, unlike the elastic neutral axis. Okay, so if your section is, in this case it's a symmetric section, so the plastic neutral axis is coming in the middle. But even if it's let's say the top flange was much bigger, then also this line will be at a place where the upper and lower areas will be equal. Okay, so that is what we have to understand from this, and that is what we will use to calculate the value of MP also. Okay, so now let's look at how to calculate directly the plastic movement for a rectangular section. Okay, so as I said, you have a section of depth D and width B, and this is the strain distribution at failure, that is at plastic hinge formation. This is the stress distribution at failure. So it directly comes as, let's say we know that CRT is equal to B into, this is my B, this is D. So area is B into D, D by 2. that is my area, into Fy. So that is my C value or T value, and C will act at the CG of the upper area, which is at again d by 4 from the neutral axis, and T will act at the CG of the lower area, which is at d by 4 from here. So multiplying these two, we get basically MP as BD square by 4 into Fy. Okay. Now this looks quite similar to our elastic bending moment of resistance, that is My we were calculating as Ze, the elastic section modulus, into Fy. So this quantity is called a plastic section modulus, Zp. Okay. So basically Zp is BD square by 4 for a rectangular section, where Zp is the plastic section modulus, and Ze for the same section is BD square by 2, which is basically nothing but I by Y max. I will be what? BD cube by 12, and Y max is D by 2, right? So it will become BD square by 6. So that is my Ze, and the factor Zp by Ze is called a shape factor. So that is the factor by which the moment capacity gets increased. So for a rectangular section it is 1.5. That means after reaching the yield moment, you can increase it to 1.5 My. Okay. So that is the value up to which you can go, at which plastification will completely occur. Okay. So that is what is. So there is a 50% reserve strength or post yield strength, as we call it, which is quite considerable for a rectangular section. But unfortunately we don't use solid rectangular sections in steel design, so because it's difficult to connect and so on. So we use what are called I channel and box type sections. So if it is an I section, let's say, how do you evaluate the plastic moment of an I section? Okay, so one option is, like before, we divide it into two equal area parts, that XX axis is the plastic neutral axis. Some people call it PNA for short, and you find the CG of this area, and that into lever arm plus the CG of this area will give you the lever arm, into area into Fy will be the C or T value. So that will be the MP. But that's a cumbersome procedure, because again you have to find CG of a complicated shape. So it's easier to rather divide this into 4 rectangles. So I have marked them 1, 2, 3, 4. The first rectangle is the top flange. The second rectangle is the upper part of the web, third is the bottom part, and fourth is the bottom flange. Okay. So each one, the first rectangle gives you a force C1, the stress resultant is C1. So here you can see C1 is the width of the flange B into thickness of the flange, BT into Fy. Okay. So that is how we get this C1, and you know it's easy to locate the CG of a rectangle. You know it is at, let's say, d by 2, that is total d by 2 minus Tf by 2. Okay. So that is the CG of the rectangle. So that C1 into this one, d by 2 minus Tf by 2, gives me the lever arm. So that is the moment contribution MP1 of the top flange. So like that we can go on adding the contribution of moment from the 4 rectangles. So the values are given here. For example, T3 is similar to the top flange. This is the bottom flange, and this web 2, that is C2, is given by this, and that into this value gives me MP2. So that goes here. So like that we can sum up and we can quickly get the MP of the cross section. Okay. So if you calculate MP for practical rolled sections, you will find that the values vary from around 1.09 to 1.15. Conservatively we normally take it as 1.12. So basically you may be saying that, okay, we will get only 12% more than an elastic analysis. True, for a cross section you get only 12%, but when the structure becomes indeterminate, you get much more benefit in terms of the load carrying capacity, right. So the collapse load factor is defined as the plastic collapse load Wp divided by the elastic yield load, that is Wy. So Wp by Wy for a simply supported beam will be the same as the shape factor, but for other beams it will be more than the shape factor. Okay, so that is where we get the advantage. Okay, so now how to analyze the beam by plastic analysis. So let's first take a simply supported beam with a single point load W at a distance A from one of the supports. So I get a bending moment MP here, and as a consequence, when I go on increasing W, when W becomes Wp, this bending moment reaches MP, and a plastic hinge forms, and the beam deflects like a mechanism. This is also called as actually rigid plastic analysis, where even though you have a bending moment here in the other parts, that means the section will bend, but that bending is very negligible. So we don't want to include that in the calculations. We are neglecting, and we are taking only the rotation at the plastic hinge as the main thing. So this becomes like a straight line. This is also like a straight line. Okay, so that means the beam is almost rigid from here to here and from here to here. Only thing is it rotates at this point now that the plastic hinge has formed. So we find that this is how the beam will deflect. This is called the mechanism method. So we know that a hinge will form here and the beam will collapse or become a mechanism. Now at this point, when it just becomes a mechanism, we equate the external work done with the internal work done. So basically compatibility tells you that if the deflection is delta, if you call this slope as theta and this as phi, the external angle of this triangle will be theta plus phi. So basically my beam has rotated by at the hinge by theta plus phi. Okay. So the internal work done is MP, rotating the beam by theta plus phi. The external work done is WP, coming down by a value delta, which is this one. You can write it as A theta, let's say. So this is the external work done. When we equate to the internal work done, we get this MP is the collapse, the MP required to avoid collapse at WP, or to just have collapse at WP. Okay. So that is the MP required. So if you are doing design, I will know what is the ultimate WP that I need to apply on the beam, for which my beam should not collapse, and I will calculate MP required, and then I will select a section with MP greater than required value. Or if I am doing analysis, I already have my beam, so I know what is the MP cross section and what is the MP of the cross section. So I can calculate what is WP. In this case, WP will be L into MP by AB, right? So that is how it will be. So notice that if you know the elastic bending moment for a simply supported beam with an eccentric point load, that is W into AB by L. Okay. So the equilibrium has not changed because the beam has become plastic. Whether the beam is elastic or plastic, the bending moment at this point will remain WP into or W into AB by L. Okay. So that is not going to change. What will change is, depending on the value of M that you can reach, your collapse load that the beam can take will change. So that is what we are looking at here. Okay. So that is how we do plastic analysis, and we get to know the collapse value. Now that is one thing. So that was a determinate structure. Now let's look at an indeterminate structure in the form of a propped cantilever. Again, it's indeterminate to the degree 1 because we have only one extra unknown. So we have an unknown reaction here. We have a load W at a distance A. So in this case, how to solve? Again, what we will do is, we don't really need to draw this diagram also. We identify that as I apply the W, there will be a large sagging bending moment under the load and a hugging moment at the support. So these are the places where the hinges have to form. So since it is indeterminate to degree 1, 2 hinges have to form for it to become a mechanism. And as a consequence, these 2 hinges have formed, let's say, and the diagram looks exactly same as what we were doing for the previous case. So again, it will be WP AB by, in fact this will be now L plus B. Why L plus B? Because the work done now, the internal work done is MP into theta at this point, at this fixed hinge, and MP into theta plus phi at this hinge. So there are 2 hinges which have to form, so more internal work is done in this case, and as a consequence the MP value will actually reduce compared to last time we had only AB by L. So if I am adding an extra B in the denominator, this value will be less than the previous case. Okay. So which means a smaller section would be adequate for a propped cantilever because it has more redundancy. Okay. So that is the advantage, but the disadvantage is, if I want to make a beam as a propped cantilever compared to the simply supported case, I need to have a connection which will take that bending moment MP here. Okay. So that becomes a disadvantage. That would cost me money, right? So that is an issue in practical designs, but generally I will get a smaller section for the beam. Okay. So that is what I am getting here, and WP by WY if you take, it will come out like this. So basically that is again coming less than 1. Okay. So you will get an advantage if you go for plastic analysis for indeterminate structures. Let's go further for a fixed beam with point load. This is a central point load that has been put, and since it has now degree of indeterminacy is 3, so 3 hinges have to form, and one will form at the midspan and the other 2 at the supports, and as a consequence MP at into theta A, some people call it ABC, and they will write this as theta A, and this as 2 theta as MP at B into theta 2 theta, and MP at C into theta. In this case we are assuming that MP is same, so we have written without suffixes ABC. So that becomes this thing, and MP becomes WL by 8, which is almost half the elastic case, okay, where you get WL by 4 in the middle. Okay. So what we find is that the support and span moments first of all become equal. In case of course in the case of elastic system also they are equal generally, but basically the bending moment diagram should not cross a value MP at any point, because that is the limit of the beam, and the largest values when they reach MP, the full collapse mechanism will form, and that gives you the true collapse load. Okay, that is the fundamental of this plastic analysis. Okay. Now plastic analysis is pretty simple when you have to tackle point loads, but when you have to tackle UDL it becomes little tricky, because we don't know under a UDL where exactly the hinge will form. Okay. So what we need to do is we need to work it out in this way. Basically here, let's assume that a hinge forms at a point X from the free end, that is the X, at this point the hinge is forming. So the work done by this part, let's say, is W into X. Okay. And if this is deflecting by delta, average deflection will be delta by 2. For it is deflecting by delta at one end and 0 at the other end. So average deflection for this entire UDL will be delta by 2, okay, or X by 2 in that case. So that is what is written here, W into X square by 2 will become the work done. So based on that we can work out that X is 0.414 L into WP, and the WP can be worked out as 11.57 MP by L square. So we can, and the corresponding bending moment diagram will be like this. It will be MP here at the support, it will reduce to 0 here, and this is the MP at midspan. So some people call this as the free bending moment diagram and the fixed bending moment diagram, and superposing the two they get the net bending moment diagram, which is what we had done in an earlier problem. Okay. So that is giving you an example of how you can solve an indeterminate beam very quickly and very easily. When it comes to a rectangular portal frame with, let's say, pinned base, again it's almost like a fixed beam, so 2 or 3 hinges will have to form for this to become a mechanism. Let's assume that it is under action of W and H. Okay, so there are 2 loads which are acting, one is the W at midspan, one is H. So what we do is we try to break this into individual mechanisms. The first one is called typically a beam mechanism, similar to what formed here in the fixed beam case. So 3 hinges forming a beam mechanism, and for that WL by 2 is the external, L by 2 into theta, if you call this as theta, the external work done, 4 MP into theta is the internal work done, MP into theta here, MP into theta here, and MP into 2 theta here. So that becomes the internal work done. Equating that we can find what is the WP at which this frame will collapse by this mechanism. Okay. So similarly, just by applying H, we will find that if 2 hinges form like this, the frame will sway and collapse. So H into H, H theta, basically this is theta and the height is H. So H into H theta is the external work done. This 90 degrees has now opened into 90 plus theta, and this as 90 has closed as 90 minus theta, right. So in both cases the internal work done is MP into theta. So right, so 2 MP theta, theta gets cancelled, so HH equal to 2 MP becomes the equation for the collapse by this mechanism. Okay. So now there could always be a third mechanism where due to the combination of H and W the frame will collapse. So this is also called a combined mechanism. the reason why it is called is you can actually get this mechanism by adding this and this. Okay. So how do we add? Like we apply both the loads, and then here we find that this 90-degree angle was reducing by theta. It was 90 minus theta. Here it was opening up by theta, so it was becoming 90 plus theta. So it gets sort of cancelled out, minus theta and plus theta. So there will be no hinge forming here, and here it is closing by theta, and here also it's closing by theta. So here it will close by 2 theta. So it will become MP into 2 theta, and here again it was sort of bending by 2 theta, and here no, right? So it is 2 theta. So MP into 2 theta. So 2 plus 2, 4 MP theta will be the on the right hand side, and that gives you a combined mechanism. And you will find that generally the combined mechanism will govern because the external work done will be more. Both the loads are now doing work together to make this frame collapse, right? So combined mechanism will give you the lowest collapse load factor. Okay. So sometimes what we do is we put a factor called lambda in front of W and H, and we say that W and H will go on increasing, which means basically if I go on increasing lambda, W and H will go on increasing proportionately, and then when they reach a certain value, that thing will collapse. So that gives you the collapse load factor lambda. Okay, so that's how we solve portal frame. Okay, now in plastic analysis, it's also easier to handle non-prismatic beams, because here we are not going to worry about compatibility or deflections or anything. We are directly going to the collapse mechanism. So if I have a simply supported beam with UDL, normally you may be knowing that even the elastic bending moment diagram will look like this, but then this value here will be WL square by 12, and this value at midspan will be WL square by 24, right? So the midspan takes much less moment and the support takes large moment. So if I have to design this beam for elastic conditions, this becomes my design moment. Okay, I have to design for WL square by 12. But then the same beam if I provide here, it will not be so efficient, and consequently it will not be an economical solution. So what I try to do is I use plastic analysis, and as a consequence I may want, like in the previous case, this case, I may want to make these movements equal, right? So if it becomes equal, then I can use the same cross section throughout. So that's an advantage I get. But that is one solution, that is one possible solution, that is you have M support and M span being equal, and if they are equal and they have to add up to WL square by 8, so they should each be WL square by 16, right? So that is how we will get. So I have to design my beam for WL square by 16, that will be my design moment. But then if I do that, I will have to design these two support connections also for WL square by 16, which may be a bit uneconomical. Okay. So what I want to do is I just don't want to look at only the beam, I am also looking at the connection design, and I want to reduce the connection cost relatively, but I still want some fixity. Okay. So what I say is, I can say that okay, at the support I will design for, if the midspan is designed for MP2, this case 2, so MP2, I will design the supports for MP2 by 2, half the movement at midspan. Okay, so I can choose any value, I can choose MP2 by 3, MP2 by 4, whatever I want, I feel is economical, I can choose that. So I am just choosing MP2 by 2 as a trial, and then I will get the same equations like MP2 by 2, or you can call it as MP at A, let us say for short, into theta, plus MP at C into theta, plus MP at B, which is this one, into 2 theta, will equate to the total external work done, and then I can work out what is the MP2 required, and I will get a beam where I need to provide, this is the largest moment from here to almost here, so I provide that section somewhere up to here, not necessarily up to the point of 0 moment, I can go beyond that also, wherever the moment is not exceeding this value, up to that I can use one section, and where I have the maximum MP2, that same section I will provide in the midspan. So I am not providing a tapered type of beam, but I am providing a stepped type of beam. Okay, and I can choose 2 different smaller beam sections. Let's say this may come out as ISMB 200 and this may come out as ISMB 300. So I will get economy in the beam design on one side, and at the same time, since I have to now connect only a smaller beam to the support, I'll also get economy in the connection design. Okay. So plastic analysis will help you design non-prismatic beams quickly and even indeterminate beams, and then you can get a very economical solution. You can also think of alternative tapered beam solutions. That is another option. I keep this as MP 2/2 and I gradually increase it from that to this value, keep it constant, again I gradually decrease it. So I can do it that way also. So that is another possibility that I have. Okay. So this is the summary of plastic theory. We come to towards the end of this presentation. Advantages of plastic analysis. Number one, it gives realistic failure loads. So as a consequence, it gives the correct factor of safety. The factor of safety which you work out for your working stress type of design using elastic analysis, they are not really correct. Okay, because they assume that the beam will fail the minute any point will reach yield. So which is not true. Okay, so you may think that it is correct, but it is not really correct. So you get larger factor of safety for indeterminate beams and smaller ones for determinate beams, which we don't want, whereas this will give you consistent factor of safeties. It gives more economical design, and it gives lot of flexibility in design, like I can go for non-prismatic sections, etc., etc. And it is easy to do hand calculations for structures with small degrees of indeterminacy. We saw even a fixed base portal frame can be quickly solved to get the solution, and it can also be used as a check against some computer outputs. Many people model these frames in let's say some software, and they give incorrect support conditions, support constraints as they are called. So if a support is, let's say, a hinge, they may release the movement, but they may forget to release the they may release the displacement. So as a consequence, that move. Okay. So it will not, from the solution you wouldn't know whether your solution is correct or not. So you can use this to check on your solution. Only limitation is that it cannot be used for members with non-plastic, and we'll see what are non-plastic sections in the next lecture. But basically sections which are liable for local buckling, in such cases it cannot be used, or members which are liable for stability failures, which we might see tomorrow, those beams it cannot be used. So in summary, use of plastic analysis gives economical design. Elastic analysis may still be required to check for deflections under service loads, that is working loads. In many structures, a separate stability analysis may also be needed to ensure safety. Okay. So with this, I conclude this presentation. Now we will have a quick session for questions and answers. If anybody has any question on this, you can ask. So I am looking at chat messages. There is a question: what are the limitations for the design for the prismatic beams? As such, there are no limitations. For prismatic beams, we can use as usual any method. It is much easier, right? Because your EI is constant. So elastic method also is easier. Whereas when beam becomes non-prismatic, either tapered or stepped, then you have to calculate what is the EI at this part, what is the EI in the next part, things like that. Whereas in plastic analysis, I am not going to calculate any of that. Only thing I will calculate is the MP for each cross section. Okay, so that is the only. There's another question. Explain lower bound and upper bound theorem. Okay, I didn't want to touch upon this because they are generally explained in most textbooks. Basically, the mechanism method gives you I think a lower bound on the plastic collapse load, because you might have chosen the wrong mechanism, right? But if you choose the correct mechanism, like we saw in the case, for example, of the PPT, we saw rectangular portal frame under W and H. So if I choose this as a mechanism, I'll get a collapse load against W, and that may not be even so. In here the H doesn't do any work. Okay, so I'll conclude that this may be the W at which the frame may collapse, but it will collapse much before that, because H also is increasing proportionately with W, right? So so I need to go for this method. I should check all possible mechanisms, and the lowest one will give me the correct collapse load. Okay, lowest load will be the correct collapse load. So that gives me the upper bound values. And in the static method, there's another method which I have not touched. we can get the other bound. And there is another uniqueness theorem which says that when the mechanism that you have chosen is the correct mechanism and all the bending moments are either equal or less than MP at the corresponding sections, then that is the true mechanism and you will get the true collapse load. Okay, so those are the three theorems that are central to plastic, but they are, I would say, more or less theoretical. So it's not really necessary to be very clear about them. If you know the method and you know how to calculate, that should be adequate for practical designs. Okay, if there are no questions, I think I prefer to move on to the next presentation. Yeah, next is the laterally restrained beams. And the contents for this presentation are the design bending strength of laterally restrained beams. Then we are going to check the beam for shear, design for shear. Then there are two failure modes called web buckling and web crushing. We have to check for these failure modes. And we have to also make sure that under working loads the deflections are within limits. Then we will look at something called built up beams and tapered beams. And we will just have a look at beams with web openings. Okay. So basically, let's look at it this way. I have a beam like this. I apply a point load. Okay. So for our convenience, we are bringing in terms like shear force, bending moment, the shear force diagram, how it varies, and then based on that we are trying to calculate the stress and all. But this is actually an easier way of doing things. The actual behavior is very complex. Okay. As far as the beam is concerned, all it knows is that the load that has been applied needs to be transferred to the supports, and it does it by a very complex mechanism. So this is actually a photo of what is called as a photoelastic experiment, where we may make a perspex beam, we load it, and then with an optical gun we can check the what I call the Moir fringes. That shows how the stress actually flows into the support. So it is pretty complex, and we are just approximating this by our theory of pure bending or whatever, right? In fact, pure bending itself never occurs because most beams have UDL where shear is present throughout. Okay, and this is what it says, screen capture of a finite element analysis of a beam subjected to a point load. Very coarse, so you don't see the stress concentration effects, but you can see it something a little bit here at the supports. So actually there will be a huge stress concentration at the point where we are applying the load. So these effects are not captured by our normal analysis, and what we are trying to do by going for this beam theory or what you call plastic theory or whatever is to capture the gross behavior of the beam, not the detailed behavior. Okay. So we are just trying to do that, and in the process there could be cases where some beams may develop some other failure mechanisms which your analysis may not be able to capture. Okay. So that is something which we need to worry about. Okay. So one typical example is due to this huge stress concentration which you can see here, local plastification can occur at that place, especially in the web and all, things like that. Then this is also called a stress analysis, right? There is a stress analysis that we have done here, but quite often the beam may have instability issues. Okay, so there are variety of buckling modes in which it may fail. So I have listed some of the failure modes of beams subjected to, let's say, vertical loading, whatever, bending. First is note that I have not listed reaching the yield as one of the failure modes, because that is not leading to failure. We have just seen that any point reaching yield stress is not going to make the beam fail, because steel beams are ductile. Okay, so they have ability to yield at when the stress reaches yield point. Okay, so it is only when the plastic hinge forms and a mechanism forms that the beam will collapse by plastic mechanism. There could be beams which, when loaded vertically, they will buckle laterally in the lateral direction, similar to column. When you apply a load, they buckle and fail. So that is called lateral torsional buckling. So that is, it involves some twisting also. We will see that tomorrow, lateral deflection and twist. The beam can also fail by local buckling, of its component elements. Typically the flange can buckle in compression, that is the flange plate locally buckles in compression. The web, if it is deep and thin, can buckle in shear. This we'll see in plate girders. The web can also buckle in compression due to concentrated loads. This also we will see today. This is called web buckling. Then there could be other local failures due to stress concentration effects. Like one is of course yielding of the web in shear, which we are going to check now for plastic yielding in shear. Then crushing of the web is also called crippling of the web, where due to the, just as I showed you here, due to huge stress concentration, local yielding will occur and the web will crush or cripple, it will bend locally like that. So that is called crippling of the web, and buckling of thin flanges. So there are variety of failure modes in which a beam can fail. Okay, and what we are going to look at in this are only a few of them. Of course, we are not going to look at this. This will be done under laterally unsupported beams. We are going to look at plastic hinge formation. We are going to look at local buckling of flange, web, etc. The web buckling due to shear we are not going to look at. Web in compression due to, this is called web crippling, we are going to look at. So we are going to basically look at plastic hinge formation of the beam, local buckling of flange or web in compression, local buckling of the web, that is basically web buckling, and web crippling and yielding of the web in shear. So these 4 failure modes we are going to look at in this presentation. Okay, so this we have seen as a basic concept for plastic analysis. What we realize here is that, let's say I have a UDL on a fixed beam. First the this bending moment here is WL square by 12, so it will reach MP. So 2 hinges will form. So the beam will look as if it's a simply supported beam with external end moments MP, MP at the 2 ends. Okay, and as I continue to increase the load, the 3rd hinge will form, right? And then the mechanism will collapse. A collapse mechanism will form. This is what I am going to analyze to get the plastic collapse load. But for this to happen, these 2 hinges have to continue to rotate, okay, and they may not be able to rotate keeping MP constant. That is, they may lose their MP if they locally buckle. Okay, so if that is the case, then the plastic analysis also will fail. So for a plastic theory to be valid, the plastic hinges should be having the locations where hinges are going to form, they should have what are called plastic cross sections. We will see that in this lecture, what are plastic cross sections and things like that. Okay, so the rotation capacity at the hinge is very important. Okay, so now what let's look at, let me see, let's take an I section like this. Okay, so if you go on bending, we are saying as here that first the flange will plastify and then the web will plastify and then the entire section will plastify and you will get bending moment MP, right? But that may not happen if the width to thickness, this is the B is the width of the flange, actually BF is the width of the entire flange, but this entire flange can be looked upon as made up of 2 component plates, B which is BF by 2 and thickness TF, thickness of the flange. So if B by T ratio of the flange is beyond a limit, then what happens is this flange locally buckles before the web can start yielding and I will not reach MP. Okay, so those issues are to be tackled. We are not going to look at local plate buckling in this lecture, so we will just use that information to classify sections, and we will say that if a section can reach MP and maintain that MP over a large rotation capacity, then it is called a plastic section. Okay, so in this case I should have actually drawn this orange line up to here and then perfectly flat. Okay, but purposefully it has been drawn a little above because sometimes beams do have some strain hardening, so it may go flat, again it may go little up or whatever, and then it may come down. But basically as long as it is above MP, we are saying that we are conservatively taking it as MP, so it is okay, okay, for plastic analysis. So it has to maintain an MP value for a large rotation capacity, phi u. Okay. Now there are, as you increase the B by T of the flange or the web or D by T of the web, what could happen is it may reach MP but it will not be able to maintain MP. So it will collapse, or it will start shedding off the MP value. Now such sections are called compact sections. So in this case, suppose I had a compact cross section for this beam. These two hinges will reach MP, but then before this third hinge can reach MP, this MP will start reducing. So it will become MP minus delta M, which will get transferred to the center. So when this reaches MP, this will be less than MP, both these things. So that means I'll have to take that value and do the plastic, which is difficult. So I don't know what is that value. So I cannot really use, because of analysis limitation, I can't use a compact section for indeterminate structures. Okay, I should not use. But I can use them for determinate structures and do plastic analysis. Okay. So generally at the section level, the capacity is MP, but at the member level, it cannot be used as for plastic analysis. So those are called compact sections. As I further increase the B by T, I may cross My, but before I reach MP, it will start locally buckling. Such sections are called semi-compact sections. So you get only this partial plastification possible in such sections. Okay, so which is what we had drawn here, partial plastification. So you can go up to here after this local buckling occurs, and you never reach this point. Okay, and sections which have very high B by T values, they will not even reach My. So even elastic analysis, the type that you are doing, is not possible for them. There are other elastic analysis methods, let's say finite element methods and all, may be able to bring that local buckling in and tell you what is this value. But since they are complicated, we will not use such sections for routine design. Okay, so slender sections will not be used in design as per the code. And if you are using semi-compact sections, you don't know this value, so you assume the capacity as My. If you are using plastic and compact sections, you can assume the capacity as MP. And only if you are using plastic sections, you can do plastic analysis. So that is what is called section classification. So based on the minute you pick up a section or you decide to make your own section, you have to do this section classification, and then based on that your entire design calculations will depend. Okay, so here this B by T, plate width to thickness ratio, is plotted in the x-axis, the moment capacity is plotted in the y-axis. So in reality this remains MP for up to beta 1 and beta 2. These are two limits. So if you cross beta 1, plastic will become a compact section. If you cross this value, compact will become a semi-compact, and the section capacity will start coming down like this. But since we can't calculate, we are going to put this line down and say that the capacity is My between beta 2 and beta 3, and beyond beta 3 it will of course gradually come down, but since we can't calculate, we are going to assume the capacity as 0, or in other words we are going to prohibit such sections. Okay. Now what are these values of beta 1, beta 2 and beta 3? They are given in the code in a table, in table 2 of IS 800. By the way, it will be helpful for you if you bring the code from tomorrow, if you have not brought it now. But table 2, this is only an extract from the table, gives you this plastic compact, semi-compact beta 1, beta 2, beta 3 limits that have to be used. Okay, there is an epsilon everywhere. It says epsilon is root of 250 by Fy. So what happens is, if for mild steel epsilon will be 1, so directly the limit will be 15.7. But if Fy is greater than 250, that is high strength steel, then epsilon will be less than 1. For example, if it is 350, this will be like 0.89. So I'll have to multiply 15.7 with 0.89, and that may come out as, let's say, 13.6 or something. So that will be my limit. Okay, so high strength steel, the limits are more stringent because the Young's modulus doesn't change, but only the stress will increase. Okay, so now how to classify the elements? The flange is called as an outstanding element. I'll go back to this cross section. So an outstanding element is one where one end is connected to another plate and the other one is free. So that's called an outstanding element. The web is called as an internal element because both ends are connected to other plates. Okay. So for different elements, whether the section is rolled or welded. Now again, why rolled or welded? Because rolled sections tend to have less residual stresses, whereas welded sections, because of welding, they have high residual stresses. Okay. So basically hot roll sections are heated, they are passed through a set of rollers to get the required I shape. Okay. So that is called the rolling process, and then the section is allowed to cool in the air. So that induces some internal stresses which are called residual stresses. Those are relatively less in rolled sections, but for welded sections we take 3 plates, weld them together. So when we weld, we heat a local area to a very high temperature, and then suddenly it cools. So it involves higher residual stresses. Okay. So compared to rolled, you can see the welded limits are lower. Okay. So all the limits, 15.7 becomes 13.6 and so on. So that is one thing. Then for internal element, depending on the type of loading, if it is under pure bending, that is neutral axis is at mid height, these are the limits. If it's under axial compression, it will be, there is no limit for these two, but 42 is the limit. For angles, circular tubes, other limits are given. So we have to take these limits and classify a section as a first step. Okay, we'll see how to do that later. Now, given that a section is plastic or compact, and if it is laterally restrained, or it can even be semi-compact for that matter, as long as it is not going to laterally buckle, okay, it's not going to laterally buckle, none of its elements should buckle until a desired limit state is achieved. That is, local buckling should not occur, limit state of serviceability must be satisfied, and members should behave in accordance to the expected performance. So basically what this says is that some unexpected failure should not occur, then we call it as a laterally supported beam. Okay. Now we will see that tomorrow in more detail. If a beam is not laterally supported, when I apply a load, it may suddenly buckle laterally and fail like this. So this is a laterally unsupported beam. So we are not going to talk about these beams today. So we are going to assume that some guide is given like this for vertical lines. So this section can only deflect downwards, it can't go laterally. Okay, if I apply vertical load, it can only come down. So that is called a lateral support. If a section is bent about the minor axis, so this is called the minor axis, YY axis, then it is a laterally supported beam. So it will not have any lateral instability problems. So then it's a laterally supported beam. So for these beams, section 8 of the code tells you how to calculate the design strength in bending as per 8.2.1. Okay. So that's what we are going to see now. So the code 8.2.1 basically reads like this: the design strength in bending or the factored design moment. So in limit state design, we take the bending moment under working loads, multiply it by load factor, and we get the factored design moment M. That should always be less than the MP is the nominal capacity divided by a partial safety factor gamma M naught, gives you the design bending moment, bending strength. Okay. So it says that the factor design moment should always be less than the design bending strength MD. Okay. And MD is, so that is what the code says. Now we want to know how to calculate MD. Okay. Now before you do that, the code says if for a laterally supported beam, there are two criteria to be checked. One is the web is stocky, that is D by TW is less than 67. You don't have to check this for standard rolled sections like ISMBs, ISWBs, all these will have stocky webs. Okay, they are rolled in that way. You have to check this only if you make your own section, and we will see that if D by TW is greater than 67, the web can have shear buckling. So that is called a plate girder. So that we will see later on, but so basically we have to make sure that it is not having a web susceptible to local buckling, shear buckling, and also the shear is low at the cross section, less than 60% of the full shear capacity of the section, which is true for most beams unless you have a beam like a cantilever where the bending and shear come at the same section and the cantilever span is small. If that is the case, then you will have fairly high shear in the at the place where the bending is coming. Okay. So for low shear case, you don't have to use this. Otherwise, high shear means you have to go to section 9 of the code, 9.2 of the code. Okay. So given that for lateral supported beam, the design bending strength MD can be taken as beta B ZP into Fy by gamma m naught. So this is how the codes are written. Actually, you could have written it in a simpler way. Let's look at it this way. Okay. So the code says beta B is 1 for plastic and compact section. So if I put beta B as 1, what would be my capacity? MD will be Zp into Fy. Zp into Fy we have just seen is nothing but MP of the cross section, the full plastic capacity. That is the nominal capacity, but since we are not very sure about getting that Fy in practical beams, we use a gamma m naught for material safety factor. So this becomes the design capacity. The minute I put this gamma m naught, it becomes D. So I am allowed to use the suffix D. Okay, so M becomes MD. Okay, or MP becomes MD. Okay, so basically MD is nothing but MP by gamma m naught for plastic and compact sections, which is what we have seen. Similarly, for semi-compact sections, if I put beta B as ZE by ZP, so ZP will get cancelled, I will get ZE into Fy. ZE into Fy is what? Nothing but My, the first yield moment of the section, divided by gamma m naught will be MDY, the design yield strength of the section, okay, which is what we are getting here. So the code has exactly told what we have just done, saying that if your sections are plastic or compact, they can reach MP. If your section is semi-compact, it will reach My, and to these two values you put gamma m naught to get the corresponding design values. Okay, and there is also an upper limit put 1.2, but as I told you, for I sections, channel sections or box sections or most standard sections which are used in steel, your shape factor will never be more than 1.2 unless it's like a rectangular solid section, then it is 1.5. So this part will govern only if you are using a solid sections, but for most other sections you don't have to worry about this check. Okay, so you can only check with this. So this is the design bending strength. Okay, so this design bending strength can be achieved provided the other failure modes are prevented. Now one failure mode which you are assuming is prevented is lateral buckling. The other failure modes which could happen is what is called as shear yielding. So if I have a very short span beam, bending moment is not much but shear force is very high, and the shear crosses the yield capacity of the web. We assume that web takes most of the shear. So if it is exceeding the capacity, then the beam will physically step down or it will yield in shear and fail. Okay, so this is shear failure, shear yielding. Some beams, the web will be thin and deep, and as a consequence, at the support or at points of concentrated loads, the web may buckle between the flanges. Okay, so now flanges are generally very thick, so the web will have to maintain a verticality at the flange. It cannot rotate about the flange, but it has to remain vertical. So that's what I have shown it like this here. And then with reference to that, it will buckle as if it's a column. Okay, under that axial compression. That is, your two flanges are getting compressed, and between that the web will buckle. Okay, so that's what can happen. This is called web buckling. And in some cases, due to the point loads, there will be stress concentration at just above the flange web junction, and that could cause web crippling. So these two again we have to check how to do. So code gives us guidelines for this. The first one, shear yielding, this one is given in section 8.4. It says that the shear in your section should be less than the design shear capacity Vd, where Vd is the nominal shear by gamma m naught, where Vn is nothing but Vp, also the full plastic shear capacity of the web. And for most sections, I sections etc., if Fy is the yield strength in tension, Fy by root 3, there is a criteria called von Mises criteria, according to which the shear yielding will occur at Fy by root 3, and that into the area under shear will give me the Vp. Okay. So here for Fy I do not have to put gamma m naught because it is eventually coming. Okay. So when I calculate Vd, Vd will be Vp, that is Av into Fy by gamma m naught root 3. Okay. So since it is shear, whenever you find shear, you always put root 3 in the denominator. Okay. And whenever you want D value, you put gamma m naught in the denominator for Fy. Okay. So where Av is the, so basically it is, this is the limiting shear stress. You can also call it as tau y if you want. Some people call it as the yield shear stress as tau y, and this W is for the web. Okay. So into Av, where Av is called the shear area. Av for a rolled section is defined as, I think it's not here, but basically it's defined as the total depth into thickness of the web, capital D into Tw, and for a welded section it is defined as the depth of the web, dW into Tw. Okay. So that is the Av is the shear area. So that is how we can check that if V is less than Vd, then this failure will not occur. Okay. So if V is greater than this may occur, and we have to make sure that something is done to prevent it by strengthening the web. Now web buckling, as I said, occurs under points of concentrated load. So even if your beam has uniformly distributed load, you have to remember that the support reaction is a point load, okay, upward point load. So if let's say this is my support of width B1, this is also called the stiff bearing length in the code. So the reaction is actually acting over this distance B1, and after that when it tries to penetrate the web, it has to, there will be something called, for roll section there is something called as a root radius here. It will not be a sudden cut like that, but there will be a gradual change in the, from the web thickness to the flange width. Okay. So that is called the root radius. So this is actually showing you the root radius. So but that is not required here. Basically we can say that this is B1, and from here the load gets dispersed over at 45 degrees. So by the time you come to this section which is buckling at the mid height, you have B1 plus N1 as the width of the member and T1 as the thickness. So I have a plated cross section of this much width and thickness T1 Tw, which will buckle obviously about its weak axis. So its weak axis is about the thickness axis. So it will buckle like this, right? So, and it is going to buckle between the flanges with this end and this end as if it is fixed. So it is going to buckle as if it's a column. Okay. So if that is the case, how to calculate the load at which this buckling will occur? The PWB, web buckling in shear, the load at which this will happen will be V1 plus N1 into the thickness, this is the area of cross section at this location, into the design compressive stress for this, considering the slenderness effects. Okay. So this is, we are treating it as if it's a column of cross section B1 plus N1 and by T1. So I can work out what is the lambda. The effective length is taken as point, that is d by root 2, okay, for fixed condition of the column, and based on that I can calculate what is root of I by y. A gives me the Ry, L by Ry gives me the slenderness. Corresponding to that, there will be a FCD in the code, section 7, as if you are designing it as a compression member, and that stress into this area, if it is, gives you the load at which the web will buckle between the flanges. Okay. So that is what we are looking at here, like this. So if this is happening, then either we need to increase this, which I can do by either increasing B1 or increasing Tw. I can increase the cross sectional area. Once I increase T, slenderness effects will come down, Ry will increase, so L by Ry will come down, FCD will increase, and this is also increasing, so PWB may increase beyond the value of the reaction. Otherwise, under that reaction the web will buckle. Okay. Otherwise I may have to stiffen the web by putting a stiffener perpendicular to the web. So I don't want this to buckle. I can put it in either this front side or back side of the web as a plate perpendicular to the web. So these are options of avoiding web buckling. And of course, as I said, you don't have to normally check for web buckling for rolled sections. Okay, they will always come safe. Similarly, web crippling can occur if the stress above the root radius exceeds the yield stress. So for that, the code says this is my thickness of the flange TF, and then the next one is the thickness of the root radius. So actually the root radius to be drawn like this here. So that is B1 plus N2, and the code says you take a slope of 1 in 2.5 from B1, and over this thickness. So 2.5 times Tf plus R will be N2. Okay, so that is N2. So B1 plus N2 into T into Fy of the web. If it is, that will be the load at which web crippling will occur. Okay, so if R, the reaction is less than P crippling, it is safe. Otherwise, it may cripple. So we have to be careful about this. That is, those are the web buckling and crippling criteria. And any beam has to also satisfy deflection limits under service loads. So the service load, let's say if it is W, the ultimate load will be 1.5 times W, depending on the load combination, dead load, live load, whatever. Again here somehow L has become lambda. So the deflection for a simply supported beam you can calculate, and you have to make sure it is L by 300 as per the code. Okay, so I'll just show you the table. The table actually says you have to limit the deflections for a type of building, type of deflection, let's say vertical for a beam or whatever, under the type of load, live load. If it is a simply supported beam under live load supporting elastic cladding, the limit is span by 240. If it is brittle cladding, the limit is span by 300 and so on. So what is this limit? Basically, if you cross this limit, some problem, distress in the structure may happen, right? This is called limiting deflection or a serviceability limit. So let's say I have a tiled floor on supported by this beam, and this beam deflects a lot. As a consequence, my tile may break. Okay, so that tile is called brittle cladding. So to avoid breakage of such tiles or RC slabs cracking, we have to control the deflection to span by 300. If I have elastic cladding, that is, let's say metal sheet which may bend but no problem, then it's only a question of the floor not remaining flat. So then I can allow span by 240. Okay, if it is a roof, then nobody is going to walk on it under normal conditions. So we can allow larger deflection. So we are allowing, when we change from span by 300 to span by 150, we are actually allowing double the deflection. Okay, for purlins and girts. Under live loads and wind loads, we can allow fairly high deflections. So this code tells you what are the deflection limits that are to be satisfied, and depending on the type of beam, you have to satisfy the deflection limits. So generally we follow a thumb rule, that is, we keep the span to depth ratio of the beam for simply supported beams between 15 and 20, so that it will clear the deflection check, and for cantilevers between 6 and 8, so that it will clear the deflection check. So these can be used as thumb rules, and based on that I'll choose a section with sufficient depth so that it will not fail in deflection. Okay, so but anyway, design is a trial and error procedure, so we have to do it accordingly. Then sometimes what will happen is we calculate something and we get a certain required MP value or ZP value for a section. And so in design, what we are going to do is, I'll just go back quickly. What we will do is, we will be given the the bending moment M, and we will be asked to choose a section. So MD has to be greater than M. For MD to be greater than that value, we will calculate what is the ZP required. So ZP will be MD by beta B Fy into gamma M naught. Okay, so that will be ZP. Once I get the ZP, I will go to the available section table, steel table, and choose a section which has ZP more than that. Okay, so in IS 800 itself, in the last page as appendix, I think J, they have given all these ZP values for various sections. So I have to choose a section which has ZP more than required value, and that will satisfy this limit state of collapse condition. Then for that, I will use the I moment of inertia whatever and calculate the deflection and clear the deflection check. Okay, and then the shear check, web buckling check, web crippling check. So these checks I have to pass. Now if I find that a suitable section is not available, let's say ISMB 300 is having a ZP, and the next one is ISMB 400 is only available, but my value comes somewhere in between, I have the option of choosing the lower section and adding extra flange plates. So these are called built-up beams. So I can add extra flange plates of some thickness, let's say 10 mm or whatever. I should normally add it in such a way that it is easy to weld the two by fillet welding. so that I don't have to do any complicated things, and then I'll get a section which is giving me the required capacity. So here I have drawn a bending moment diagram, and I have chosen a purple section which has a ZP capacity only this much. Okay. So capacity is less than the bending moment, so it is not safe over certain region. So I want to add these flange plates, and for this cross section when I calculate ZP and MP or MD, I will get a capacity which is more than what is required. Okay. So my beam capacity is this one here, and then it reduces to this, and then it goes like this, so that it is always above the required capacity. Okay. So that is how I have to design the beam. I may extend this plate a little beyond, so that the force developed can be developed by welding it to the existing flange beam. Okay. So like that I can bring this a little like this and do for safety reasons. Okay. So that adequate welding shall be done to take longitudinal shear between the flange plates and the I section. So when you do this, there will be a longitudinal shear equal to area of the flange plate into Fy. So you should have enough welding between the two sections to take that longitudinal shear, and this is how we can do that. Okay. So we can calculate the ZP of the flange section alone. This anyway I get from the steel table, ZP1. This will be AY into Fy into this distance. Okay. That will give me the contribution to ZP1 for two flanges. So multiply by 2, that will give me ZPP of the flange plates. Okay. So ZP of the I section plus ZP of the plates gives me the total ZP, and then into FYD. FYD is Fy by gamma m naught, gives me M2. So M2 should be greater than the corresponding value there in the middle. Okay. So that can be done. Then you know that in simply supported beams, you have a parabolic bending moment diagram, or in a cantilever you have a triangular bending moment diagram, and so on. So I don't have to have a prismatic section. I can taper the section according to the bending moment diagram and achieve more economy. Okay. So web tapered beams are often used to strike a balance between weight, fabrication cost, and connection cost. So I'll have some fabrication cost to make a tapered beam. So I have to make sure that what I save, I should not lose in fabricating the beam. Okay. And I should also save in the connection cost. So this is an example where typical I section is taken. We just cut it like this in an inclined way, and then we flip one of the portions. So when I flip, this depth will come and sit here. So I'll get a very deep beam here and a very shallow beam. This lower depth will come and sit here. So I'll get a tapered beam with a top flange and a bottom flange, which I can use as a cantilever. Okay, with a fixed end at the deeper end. Okay, so that way I can save on steel. So that is also an option. And then quite often in real buildings we need to provide openings for service lines. Anytime your beam is more than, let's say, 300 mm deep, more than an ISMB 300, you need to have some openings. Otherwise the service lines will have difficulty. They have to go around, and that will eat up on the floor to ceiling height also. Okay. So this shows how these pipelines, these other pipelines are all able to go through these openings. Normally beams will not have so many openings, but it is a good idea to provide one small opening towards the support, right? Because of course to provide an opening at midspan would have been better, because shear force is 0 at midspan, and support, and near the support shear force will be more. But if we can provide a circular opening, generally they prefer openings near the supports. Okay. So this is the summary that we have just gone through of how to design a beam for flexure, how to avoid local buckling by choosing a proper cross section, and depending on the section how to calculate the flexure capacity, how to ensure that shear, web buckling and web crippling are not occurring, and the deflections are satisfied. So now it's open for questions. Okay, there is a question here which says width of support is 400 mm, then what will be the B1? Basically whatever is the support width will be the B1, but normally we may not get such huge widths as 400 mm in the support. Okay. So normally we will have much smaller, like the beam may be sitting on a what is called as a seat angle. So then the width of the angle will be, or even less than that, because the beam will not be touching the column flange, it will be a little away. That is something called as a tolerance gap of 5 to 10 mm given. So then the actual seating length, stiff bearing length will be much smaller. Practical example of laterally restrained and unrestrained situation, maybe I'll give you tomorrow when we talk about laterally unrestrained beams and how to restrain them, etc., etc. No questions. So I think we'll close the session if there are no questions. If you think of, yeah, one question is there. Is there any empirical formula to check for local buckling? Actually, the B by T limits are the checks which we are doing. They are all empirical, and they are not exactly theoretical. So what we do is we just take the flange width, half the flange width, divide by the thickness, so we get the B by T value. And if it is within semi-compact limit, then the section is, the flange is semi-compact, and so on. And when you classify a beam, you have to classify the flange and the web. Let's say flange is compact and the web is semi-compact, then the beam section will be classified as semi-compact, the worst of the two. Okay, so that is also to be done.